Yeah, so thank you for the introduction. As he said, I am Daniel López. I work as a machine learning engineer at Pix4D. And today I would like to talk about how photogrammetry and machine learning work together at Pix4D to basically streamline the cell tower inspection workflow. In case you don't know, Pix4D is a Swiss company which was founded here at EPFL in 2011. But since then it has grown a lot, and today we are more than 200 employees across different countries. Yeah, and we are part of the Parrot group, actually. Yeah, and mainly we are in the business of photogrammetry, but we also do research and development on other related topics. And in particular, we have a machine learning / advanced analytics team where I work. And we basically develop machine learning features for the photogrammetric tools of the company. In particular, in the past couple of years, we have been looking at the cell tower inspection problem. I don't know if you have noticed, but cell towers are basically everywhere. And yeah, the traditional workflows to inspect them involve having a human technician climb into the tower and making visual observations, checking if everything is correctly set up and connected, and then creating a report with all of this information. But of course, this workflow is very dangerous for the person climbing to the tower because, yeah, those towers are very often not very friendly structures to climb. And also it is, of course, a time-consuming process that is not easy to manage and to scale to a large number of locations. And even worse is that you can end up with really low-quality data, in the sense that it is quite easy to miss something when you are up there, and yeah, then you are back at the office and you notice that you forgot to check something, you forgot to make some measurement, and there's no way you can get that measurement. You need to go back to the location, climb again, and yeah, this is not very nice. And also these inspections need to be taken or need to be made regularly, maybe every year or so. So yeah, this is a really big problem for the owners of the towers, and yeah, being a company focused on photogrammetry, we thought this could be applied in the problem of cell tower inspection. So in case you're not familiar, the photogrammetry process, if you want, basically consists of combining the information from multiple images to create a 3D model of some real-world object. So basically you take those pictures of this real-world object, and then you find key points in those images. And by triangulating the locations of those key points, you can basically understand what is the structure and the shape of the 3D real-world object and create this 3D model. And as you will see in the presentation, this can be super useful to inspect assets like cell towers, but also other things like bridges and other infrastructure. So yeah, we are basically proposing a photogrammetry drone-based workflow to streamline the cell tower inspection process. The first step in the process is basically, instead of having a human being climb to the tower, you go to the location with a drone, you fly the drone, you take a lot of pictures of your asset, and then you basically upload those pictures to a web interface, web-based application, which is called Pix4D Inspect. And basically, we will provide you with a digital twin of your asset that you can use together with the images to do the inspection. So you can try to find anomalies in the tower. You can find defects. You can schedule fixes in the equipment and things like that. And you can generate basically PDF reports to share with the other stakeholders involved in the cell tower. Another important point is that you can do multiple inspections over time of your asset, and this is a huge advantage because you can always go back in time to check if something, for example, was fixed as a schedule or if new equipment was installed. So yeah, you can always go back in time and do additional measurements that you forgot to do, which is something that you cannot do with a traditional inspection workflow. We also offer tools basically to manage multiple assets. So if you own several assets across different locations, you can always keep track of them with a map view and all the tools that you need for that. So yeah, let's have a closer look at the workflow. As I was saying, the first step is just going on location with a drone, with a tablet, and instead of climbing to a tower, you just take the drone and take pictures of the cell tower. The nice thing about this process is that it's partially automated thanks to the Pix4D scan app that we developed. So the idea is that the pilot of the drone only needs to set some initial parameters, like the location of the asset or the distance that you want to fly from the tower. And then the Pix4D scan app takes over and basically controls the drone as it is flying around the tower. This is very important because it makes sure that the data acquisition process is completely standardized and is reliable. And also it makes it very easy to do the inspection or to do the scan of the tower very fast. So you can usually scan a tower in half an hour, more or less. So after you have scanned the tower, you have all of those pictures of the asset. What you do is you upload them in the Pix4D Inspect website, and after a while you are presented with something like this. So on the one hand, we give you the 3D model or the digital twin of the cell tower, and on the other hand, you have the images that the drone took during the flight. The 3D model is very useful because it gives you the context. So you can navigate around the cell tower, you can always keep track of where you are or what you are looking at, and you can make sure that you are not forgetting about any equipment or any part of the asset. And at the same time, on the right, you have the images, so you can really zoom in and look at the details. So if you are looking for very specific things like loose bolts or rusty spots, which are maybe difficult to find in the 3D model, you can always zoom in and see the detail in the images. But these two views are always kept in sync, so you can basically take advantage of both views of the data. Another interesting thing that you probably want to do if you are inspecting a cell tower is keep an inventory of the installed antennas and equipment in the cell tower. So you can try to manually annotate all of those antennas in the cell tower, but it's going to take a lot of time because towers are usually packed with antennas. But even if you wanted to invest the time in doing that, the result is probably not going to be super reliable, basically. And as you probably know, the orientation or accurately measuring and tracking the orientation of the antennas is very important because it has a huge impact in the signal quality for the final customers. So we have been basically working on an automated workflow that allows to detect the antennas in the cell tower and also measure some key, let's say, physical properties of the antennas, like the orientation and the size. So here you have like an outline of the pipeline. The inputs for the pipeline are the point cloud of the cell tower and the images that the drone took. And then the first step of the pipeline is basically a 2D semantic segmentation model. So this is nothing particularly special. You can use UNet or whatever other fancy deep learning architecture to segment the images. But the idea is that you find the pixels in the images that correspond to the different types of equipment items in the cell tower. And then the next step in the pipeline is what we call the lifting module that basically takes the segmentation masks produced by the semantic segmentation module and lifts that information or projects that information to the 3D model so we can segment the actual antennas from the point cloud. You might wonder why don't we use like a full 3D machine learning approach. There are several reasons for that, but one of them is that in order to identify or tell some types of equipment items, you really need the details and the information that you have in the images, which is not fully present in the point cloud. So yeah, it's similar to how the inspector needs to check the images sometimes to see some things which are not visible in the point cloud. And then the final step is what we call the alignment, where we take each of those segmented items from the point cloud, and we try to basically measure as accurately as possible the orientation of the antennas. Yeah, so let's maybe have a look at this pipeline in more detail. As I was saying, the first step is quite conventional. We just use some semantic segmentation model to find the antennas in the images. And then what we do is we take advantage of what we call the calibration information. So one of the outputs of the photogrammetric pipeline that creates the 3D model from the images is that we have information about the position and orientation of the cameras. So we know where the drone was in a space and how the camera was oriented and when it took each of the pictures. So we can use this information to somehow translate or project the 2D semantic segmentation masks to the 3D model. So basically what we do is we take the points in the point cloud and we project them on the image plane. And basically we can select the points from the 3D model that land or project on pixels of the image that have been classified, for example, as panel antennas or microwave antennas or the different types of equipment that we can detect. And the nice thing about this approach is that we don't have only one image for each item in the cell tower, but instead, because the drone is flying around the tower taking multiple pictures, we can combine the semantic segmentation extracted from multiple images to fully segment the different equipment items in the point cloud, even if they are, for example, partially occluded on individual images. So yeah, once we have fully transferred the semantic segmentation information from the images to a 3D model, what we try to do is basically isolate the particular antennas. So first, we get rid of the background part of the tower, so the structure, everything that is not an antenna. And then we use a spatial clustering algorithm to isolate one antenna, one item, for example, in this case, a panel antenna. And then the next challenge is to accurately measure the angles and the pose of this antenna from the cutout, which is not trivial. So you might want to try something like PCA or some other off-the-shelf algorithm, but the problem is that you will get an estimate of the orientation of the antenna or the pose of the antenna, which is not super precise. So one way of visualizing the orientation of the antenna is with a wireframe or a bounding box, like the one that we have here. So yeah, with traditional algorithms, you will get something like this, which is visibly not correctly oriented. And this is in part because antennas are not easy to reconstruct in 3D because they tend to be uniform in color and not have a lot of texture. And this is precisely what the photogrammetric pipeline uses to reconstruct the object. So you can find antennas with large holes in the 3D reconstruction or with blobs of noise in front of them. This doesn't help PCA. So basically, we had to develop an ad hoc heuristic search algorithm that analyzes the symmetry of the antenna cutout on different planes, and based on that, finds the best possible estimate of the orientation of the antenna. So yeah, once we have done that, we end up with something like this, a bounding box that more or less fits the orientation of the antenna, and we do the same thing for all of the items in the cell tower, basically. So we can present our users with a lot of different measurements on each of the equipment items. So for example, for panel antennas, we will report the down tilt, the azimuth, the plumb, the dimensions of the antenna, and the height from the ground, which I guess is useful if you want to plan how much cable you need to connect the antenna to the base of the tower, for example. We also try to sort this automatic inventory in a semantic, meaningful way, in the sense that we don't want to provide the antennas in a random order, and then when the user is just checking them one by one, he will be jumping all around the tower. So instead, we try to cluster the antennas in nests, and then we present the antennas maybe from top to bottom, clockwise order, or something like that, so that you have a nice experience if you are just going through the detected antennas. And yeah, this is precisely what we present our users with in the front end. So the inventory with all of the detected equipment items, and also we allow our users to add additional information about the antenna. So for example, the model, the weight, the frequencies, things we cannot infer from the images or from the 3D model. But we really try to go the extra mile to automate as many aspects of the inspection as possible. So recently we noticed that our users were spending a lot of time just selecting for each of the items a good image where this item is visible. So we try to automate this process as well, and now for each of the items that gets detected, we have an automatic algorithm that finds the the best image where you can check this item, and also defines a region of interest within the image, so that for each of the antennas you will have this nice image added to the PDF report. Yeah, so as you can see, this connection between the 3D and the 2D worlds is a key aspect of what we do at Pix4D. It is also something that helps us a lot in our internal processes. So for example, imagine the case of training a semantic segmentation model. Probably you know that in order to achieve a good model, particularly if you're going with deep learning, you need thousands of annotated images, and this is super time consuming. So we can take advantage of this by instead annotating ones in 3D and projecting the annotations to 2D. So this is more or less similar to what I was describing before for antenna detection in 2D and then lifting to 3D, but it's a bit in the opposite direction. We start with a point cloud of a cell tower, and we have somehow annotated all of the antennas or all of the equipment items that we want to be able to detect in the future. So what we do is we take those points, the points that belong to the antennas, and thanks again to the calibration information, we can project those points on the image plane. And we can select the pixels from the image on which antenna points landed when we projected them to 2D. And by selecting those pixels, we can basically create a segmentation mask that we can use to train a semantic segmentation model, basically. So as you can imagine, this saves a lot of time, because instead of annotating each antenna on 500 images, we just need to annotate the antenna once in 3D, and we get these nice segmentation masks on the fly. But also gives us a lot of flexibility in how we define the annotations, because traditionally you have to decide what and how to annotate when you start the annotation campaign, but here we can just decide how we want to handle several aspects of the annotations on the fly just before the training, or just before each training experiment. So for example, I could decide to include or not antennas which are not facing the camera for a particular training experiment, or I could decide to use or not a particular type of antenna in the training. All of those things we can decide just before we do a particular training experiment without having to re-annotate anything. And this gives us a lot of flexibility, basically. And this is in part why we have been able to collect a quite reasonable training data set with 64,000 images, more than 170 cell towers, basically all across the globe. We have some cell towers in the desert, some cell towers surrounded by snow. So we have a good variety on the data. And also we have more than 2,500 different equipment items annotated in our training data set. We also try for the users, for the final users, to take advantage of this 2D, 3D connection. So one way in which we do that is, for example, by allowing our customers to make annotations on the images that then we automatically transfer or project on the point cloud. So again, you can find very specific and very small defects in the cell tower on the images, for example, loose bolts or whatever, and then those get projected to the 3D model. So this is very interesting because you have the images to really check the details and check the small things in the cell tower, but you also have the 3D view where you can see all of the annotated defects. So you don't have to check 500 images, or if you send the inspection to another colleague, he doesn't need to check 500 images. He can just have a quick look at the 3D model and find all of those defects that you have annotated. And then, of course, you can click on one of the defects in the 3D model, and you will see the corresponding image annotation. But this is also useful for us in the sense that it allows us to understand what aspects of the inspection process our customers need to have automated. So, for example, recently we noticed that a lot of our customers were annotating Rust in their cell towers, so they were interested in finding rusty equipment in the tower. So yeah, we started looking into this problem, and basically we follow a similar approach to what I was describing before for antenna detection. We have a 2D semantic segmentation model that detects rust on the images. And we basically take those semantic segmentation masks and project them to the 3D model. And we create a version of the point cloud where we basically highlight regions or parts of the point cloud where we think there is rusty equipment, and this allows the final users to just check those highlighted regions and click on them, and we will show a pop-up with a real image of this part of the tower, so they can really assess or decide if those things need to be fixed or if they are okay with that. Yeah, and you can imagine that this is much faster than, for example, having to check 500 images trying to find a rusty vault. And yeah, I think that's everything I wanted to tell you. Just one thing, we are hiring, so if you know someone who could be interested in cracking this type of issues, don't hesitate to contact us. And yeah, thank you very much for your attention.
Thanks a lot, Daniel. Are there any questions for Daniel?
Thanks for the talk. I have a question about the models that were used to process the images. Was it like, did you develop everything from scratch, or you kind of did transfer learning somehow? And if so, what kind of libraries did you use for the whole image processing kind of? Thanks.
Yeah. So whenever we can, we use transfer learning, especially at the beginning of the project, because as in many machine learning projects, at the beginning we didn't have a lot of data. So yeah, for example, we are using transfer learning from ImageNet trained neural networks and stuff like that, and we played with different architectures, backbones. Yeah, but in the end, it's just a semantic segmentation model, like any other. As in many cases, most of the improvements that we could get come from improving the quality of the data and the amount of data, and not so much playing with this or that architecture or transfer learning or weights or whatnot.
A non-technical question, but I'm curious, how long did it take to go? It looks like a very polished product. How long did it take to get there?
Just the machine learning part, maybe 2 years, more or less. And but I think the work on the front and back end and all of that started 3 years ago. But yeah, we have been in production for maybe 1 year, rough numbers.
I also have a non-technical question, more out of curiosity. How many telcos have you been working with here in Switzerland and outside Switzerland? And because you said that you labeled a couple hundred, I mean, you represented in 3D a couple hundred antennas, but are all of these from one telcos in many countries, or did you work with several ones? Did you have concrete tests with people from telco companies who use your products? Just some numbers there.
Yeah, I don't have the specific numbers on the top of my head, but we definitely work with multiple customers and multiple telco players. So those 100 and something towers are just the ones that we use for training. But at the moment, we have had several customers using the platform and processing many more towers. So yeah, and that's, I think, very important, because there are some things that you only start noticing once you have multiple real-world users using your platform. So when it is our trained pilots that use for example, the drone to take the pictures, you can really rely on a very standard and nice data acquisition process and pattern. But the moment that you have real users using the platform, things can change a bit. So yeah, for us it's super important to get feedback from as many customers as possible.
Okay, one final question in the interest of time.
Hello, thanks a lot. I was wondering, like you said that like in order to generate new data, you take like the 3D model of the antenna and then like you project this one on the 2D image. I was wondering, like, do you also create images like with synthetic data, or Like, do you take like the real 3D model and then like you project the real 3D object, or like the one that you project is actually a 3D synthetic antenna, let's say?
Yeah. So we used, especially at the beginning of the project, some synthetic antennas, not only for the training of the semantic segmentation model, but also to do some other things or to optimize some other parts of the pipeline, like the alignment algorithm. But we tried to move away from synthetic data as soon as we had access to real data, because really in the end, the data acquisition process has a lot of subtleties and things that can influence the quality of the data. So maybe it's a sunny day, or maybe there's wind or snow in the background, and then the tower is super underexposed. So those things are very difficult to really model and capture with synthetic data. And the moment you have a good amount of real data, I think it's better to use that. But we, of course, use data augmentation techniques, several types of augmentation techniques to augment the amount of data that we have.
Thanks a lot.
Then thanks a lot, Daniel. That was a very interesting talk.